We'll start this lecture by proving the one remaining piece of proposition 21 in section 14.4. So remember the setup. We let K1 and K2 be two Galois extensions of the field F. We proved in the last video of the last lecture that K1 intersects K2 is Galois over F, and that the composite of K1 and K2 is a Galois extension of F. And our goal now is to describe what is the Galois group of this composite over F in terms of the Galois group of K1 over F and the Galois group of K2 over F. And what we'll show is the Galois group of K1, K2 over F is isomorphic to this group H, which consists of pairs sigma comma tau, where you take sigma and you restrict to K1 intersect K2, you take tau and you restrict to K1 intersect K2, and you get the same automorphism. Okay, this doesn't really make sense because I haven't actually told you what sigma and tau are. Sigma is an element of the Galois group of K1 over F, and tau is an element of the Galois group of K2 over F. So this H is a subgroup of the direct product Galois K1 over F cross Galois K2 over F. And it consists of all pairs sigma comma tau, where you take the restriction of each of those to K1 intersect K2, and what you get is the same automorphism. Okay, so the proof here is going to depend on properties of one special map. So let's consider this map phi, which takes an element of the Galois group of K1, K2 over F, and sends it to an element of the direct product Galois K1 over F cross Galois K2 over F. How does it work? You take sigma to sigma restricted to K1, comma sigma restricted to K2. Okay, first, this map really is well defined. If you take an element of the Galois group of K1, K2 over F, that is an automorphism of K1, K2 fixing F, and you restrict it down to K1, why do you get an automorphism of K1 fixing F? Well, I mean, it certainly fixes F. What you're getting, it's clear that what you get is an injective field homomorphism from K1 to somewhere. You're getting an embedding of K1 fixing F. But since K1 over F is Galois, every embedding of K1 fixing F is an automorphism of K1 fixing F. So you really do get an element of this Galois group. Same thing for K2 over F. K2 also Galois. Okay, so this map is well defined. Why is it a homomorphism? Well, just think about what happens when you apply phi to sigma 1, sigma 2. You take sigma 1, sigma 2, you restrict to K1. That is the product of sigma 1 restricted to K1 times sigma 2 restricted to K1. You can check the details. Okay, so the next thing we're going to show is that this homomorphism is injective. So what does the kernel consist of? It's all the elements sigma in the Galois group of this composite over F, where you get sent to the identity over here. But what is the identity over here? Well, the identity of Galois K1 over F is the trivial automorphism of K1. Identity of Galois K2 over F is the trivial automorphism of K2. So what is true about sigma if it gets sent to that identity? Well, it's all the sigma for which sigma restricted to K1 and sigma restricted to K2 are trivial. So sigma fixes K1 and sigma fixes K2, but then sigma fixes the composite also. So that means that sigma is trivial on all of the composite K1, K2. And that is the identity, the trivial automorphism of K1, K2 over F, Galois K1, K2 over F. So we've seen that phi is injective. Okay, so what does that mean? First isomorphism theorem, Galois K1, K2 over F is isomorphic to the image of sigma. Sorry, the image of phi of this map. All right, so in particular, this Galois group's isomorphic to its image. The order of this Galois group is the order of the image. This is a fact that we're going to use in the proof, so I want to highlight this. Where does this image live? So it's some subgroup of this direct product of Galois groups. Let's take something in the image. It's of the form sigma restricted to K1, comma sigma restricted to K2. And let's see that it's actually in H. So what we want to do is say, let's take sigma restricted to K1 and restrict it to K1 intersect K2, take sigma restricted to K2 and restrict it to K1 intersect K2, are those equal? And the answer is yes, because sigma restricted to K1 restricted to K1 intersect K2 is sigma restricted to K1 intersect K2. And that's the same thing as if you take sigma restricted to K2 and you restrict to K1 intersect K2. So what we're seeing is this pair is in H. So the image of phi is contained in H. What we want to show is that the image of phi actually is equal to H. And that'll complete the proof, because we know by the first isomorphism theorem that the Galois group of K1, K2 over F is isomorphic to its image. So if we show that the image is equal to H, we're done. So I'll pause and erase, and we'll do this last part of the proof. Our goal is going to be to show that the size of the image of phi is equal to the size of H. And therefore, the image of phi will be equal to H, because we've already shown that the image of phi is contained in H. So if we have two finite sets of the same size and one is contained in the other, then they're equal. Okay, so the big idea is going to be an isomorphism extension statement. We have K2, K1 intersect K2 is a subfield, then we have F. And we know that K2 over F is Galois. So part of what we saw in the fundamental theorem is that K2 over K1 intersect K2 is Galois as well. Since this extension is Galois, the number of elements tau, the number of automorphisms of K2 fixing F that extend a given automorphism sigma of K1 intersects K2 fixing F is the order of this Galois group. It is the degree of this field extension. So this is something that we proved when we were talking about, in our argument that was showing that the splitting field of a separable polynomial over a field gives a Galois extension. We had to talk about the number of automorphisms of one field fixing another that extended a given, or the number of automorphisms of one field that restricted to a given automorphism down below. Okay, so this is the big observation. It's this thing about the number of isomorphisms, or really automorphisms, extending a given automorphism. So what does this mean? Let's take an element of the Galois group of K1 over F, and we can look at what the restriction is to K1 intersects K2. It's some automorphism of K1 intersects K2 fixing F. Now we're going to apply this observation. There are the order of Galois K2 over K1 intersects K2 elements tau in the Galois group of K2 over F, for which the pair sigma comma tau is in H. That is, we just want to make sure that tau, it's an automorphism of K2 fixing F. We want to make sure that when you restrict down to K1 intersects K2, you're getting the particular automorphism sigma restricted to K1 intersects K2. Okay, so that is, we're counting pairs sigma tau such that sigma restricted to K1 intersects K2 equals tau restricted to K1 intersects K2. And this gives us a way to compute the order of H. The order of H is, well, when we just make a choice of sigma in Galois K1 over F, that's how many choices we have. And then given a choice of sigma, how many taus are there such that sigma tau is in H? It's the order of the Galois group of K2 over K1 intersect K2. Okay, so this is how large H is. And now we're going to use this corollary 20 from last time. K1 and K2 are both Galois extensions of F. So we're in the setup where we can apply this, right? The idea was we had an extension K of F that was Galois over F, and then we have F prime over F, any extension of F. Here they're both Galois. We can certainly apply this formula for the order, the degree of the field extension K1, K2 over F. So the degree of this extension is the product of the degrees K1 over F times the degree of K2 over F divided by the degree of K1 intersects K2 over F. Okay, this is a statement which has degrees of field extensions in it. This has the order of Galois groups. But if you have a Galois extension, the degree of that field extension is the order of the Galois group. So what does that mean? Here, this order is this order. This order is the degree of K2 over F divided by the degree of K1 intersects K2 over F. Okay, so that says that the order of H is the order of the Galois group of K1, K2 over F. And now, that's not what we were trying to say at the beginning. What we were trying to say is that the image of phi, the order is the same as the order of H. But we know that this Galois group of K1, K2 over F is isomorphic to the image of phi. So they have the same order. So now we just recall that they have the same order. This is something we said earlier. And now we see that the order of H is the order of the image of phi. So the image of phi is H, and the first isomorphism theorem completes the proof.